Good morning, students. Welcome to the mass transfer course. Today will be lecture 7. In lecture 6, we discussed about the fluxes in two processes. One is diffusion of A through non-diffusing B, and another was counter diffusion. And there are two things: equimolar counter diffusion and non-equimolar counter diffusion. And for diffusion of A through non-diffusing B, we calculated the fluxes of A with various driving force. For gas phase, this is the flux when my driving force in terms of pressure, and this is for when driving force is in terms of mole fraction, and this is in terms of molar concentration driving force. And similarly for liquid phase, this is for molar concentration and this is the mole fraction. So we saw the different ways to calculate the fluxes as per the different driving forces. And for equimolar counter diffusion, we have seen this is when it will for gas phase, when it will be partial pressure is the thing, and Ca0, so that is for it will applicable for both gas phase and liquid phase, and this will be applicable for gas phase. For mole fraction is the driving force, and this is the thing. Today we will solve two problems based on these fluxes. So first problem is diffusion of A through non-diffusing B. What is the problem statement? In a sulfuric acid plant, the air used for burning sulfur must be dry. Drying of air is done by counter current contact. Okay. Counter current contact with concentrated sulfuric acid in a packed tower. So you know sulfuric acid plant, the reaction is very simple. Sulfur plus oxygen, sulfuric acid, sulfur dioxide plus half of oxygen, sulfur trioxide plus sulfuric acid oleum, then oleum to water, then sulfur 2 molecules sulfur. You know this thing. But when there will be a reaction between sulfur and oxygen, and that oxygen will come from air, that must be dry. If there is some water is available, then it will create the problem. That's why you have to remove the water vapor to make it dry. No water vapor should be there, so that oxygen and nitrogen will come and it will react with the sulfur. Now to remove this one, easy procedure, because sulfuric acid has a very affinity to absorb water. So you pass that, because sulfuric acid is my product. So whatever air I will have, I will pass it within the sulfuric acid. The air will be absorbed, so that I will get the dry gas. So I don't need any other arrangement for drying this. Sulfuric acid, the product itself is sufficient. Now what way I am doing? I am doing in a counter current. So counter current means, so there is a vessel, okay, and packed bed, okay. So let's check this one, okay. Just I am drawing one, but it will be full of this type of packing material, okay, because to increase the surface area of the interface, it is done. Okay. So counter current means, now what is happening? So from top I am putting the sulfuric acid, and from bottom I am putting the air. And from top what will come? What will be absorbed? So dry air. Dry air will come here, and then from the bottom that sulfuric acid will come with small amount of water. Very simple arrangement. This is counter current. Okay. So drying of air is done by counter contact with concentrated sulfuric acid in a packed tower. So this is the arrangement. Okay. At a particular section of the tower, the relative humidity is, let's say this is one particular section. Okay. At section of the tower, the relative humidity is 30%. And temperature is 35 degrees centigrade in a particular point. So this is the condition, 30 degrees centigrade, 30% is the relative humidity, and the temperature is 35 degrees centigrade. If the moisture in the air diffuses to the surface of the acid through a stagnant film of thickness 1.2 millimeter. That means if you have a, let's take, this is one packing material, okay. So and this is the solid, and with their air, the liquid is falling, so there will be one solid liquid interface. Okay, this is a solid liquid interface, and above this one there will be one gas liquid interface, and this gas liquid, that interface is there, and this thickness is 1.2 millimeter. That means one solid, the pebbles is there, one solid material, okay, packing material. So liquid is falling from the top, so it will cover the solid material, okay, and so therefore there will be one gas, a solid liquid in that interface will be there, okay, and gas is coming from the top, and what will happen? So gas is when passing, so there will be contact between this liquid, sulfuric liquid, and this gas is passing, and that interface is 1.2 millimeter thing. So here this is the gas, and here liquid sulfuric acid. Okay, if the moisture in air diffuses to the surface of the acid through a stagnant film of 1.3. So this is the stagnant film is there 1.3. Calculate the flux of the moisture of at the given section, means in this section the partial pressure of the moisture at the acid surface is 0. now বলছে partial here is 30% humidity, but at this point that partial pressure is of moisture is 0. why it is 0? because moisture has a very high affinity to absorb it. So whenever the moisture will come, immediately it will be taken out by the sulfuric acid. That's why no moisture will be left here, and that's why there won't be any partial pressure. The partial pressure of moisture at the surface is 0 because the concentrated acid has an extremely high affinity for moisture vapor. Full stop. The vapor pressure PV in bar of water is given by Antoine equation ln PV equal to 13.8573 minus 5160.2, where T is in Kelvin, and DAB at 35 degree centigrade it is given. DAB at 35 degree centigrade is given. Diffusivity water A through B at 35 degree because my operating temperature is 30°5, and here also given, that is 0.2728 semi-SCM/s. Now question is, how will we deal this problem? Now first we have to identify this problem, whether it is diffusion of A through non-diffusing B or equimolar counter diffusion. Sometimes here if you see the is done by counter current contact. So counter current contact is this. So then you can tell that this is a counter current, but actually this is the diffusion of A through non-diffusion. Why I am telling? See, this is the macroscopic. If you take the microscopic view, although it is okay, this is sulfuric acid coming from the top and air is going from the bottom, and when there is interface between this sulfuric acid and air, now if you see, moisture is moving from gas phase to liquid phase, but air, that mixture of nitrogen and oxygen, it is not diffusing from gas phase to liquid phase, because this is not diffusing. So air is not diffusing, and moisture is diffusing. You have to see what is happening at the interface. Gas liquid interface is there. Here moisture is diffusing, air is not diffusing. So this is the case of diffusion of A through non-diffusing B. So you should not confuse with this one. This is counter current, okay. It is from macroscopic point of view, but you have to consider what is happening at the gas liquid interface. When two phases are there, what is happening here? If you here, each case is happening diffusion of A through non-diffusing. So generally people do the mistake here. If I made this problem statement diffusion of A through non, that's why you may tell, but you should have a very clear idea so that you should not confuse with this statement. You have to see that whether it is diffusion of A through non-diffusion based on the what is happening at the interface. Interface means two phases are there, and interface will be there. With the interface, if what is happening, accordingly you have to tell why that is. In this case, this is diffusion of A through non-diffusing B. Okay, and I told that and this is the stagnant layer. So my point 1 PA0 is this, and PAL will be this point. Okay, PAL, this is the partial pressure of moisture PAA 0, and this will be this PAL at 2. Okay, and to calculate the vapor pressure, this we know that this is the Antony equation. Familiar in your thermodynamics knowledge, this is the equation, and DAB is given at 35 degrees centigrade. Okay, so you need not to worry. Okay, so for this one the calculation is, so identification of the problem, it will fall under which category, that is very important. I told that one. So it may be the diffusion of A through non-diffusing being, or equimolar counter diffusion, or non-equal. Equimolar counter diffusion, non-equal, it is very similar, only that you know that counter diffusion, that stoichiometry is the different. But first you have to identify your problem, it will be under which category. So in this case, this is diffusion of A through non-diffusing B. Now this thing is very easy. Temperature 35 degree equal to 308. Vapor pressure of water. So I use this equation. So vapor pressure is, this is PV, I told this is in bar. Okay, it is in bar. So accordingly you have to look this. This is equal to 0.50552 bar. So this is the vapor pressure of water. Now relative humidity in the bulk is 30%. So this is when it is 100% will be there, then this will be the vapor. Only the water, then that will be the pressure, but 30% that humidity is there, then that is the 0.03 of this vapor pressure. So this will be 0.01656 bar. This will be the vapor pressure of moisture in air, and remaining will be the vapor pressure of air. That will be PA0. Okay, and partial pressure of the moisture at the acid interface, PAL, that will be 0. Already I told, because when this, in this case, that PA0, this is PA0, that PAL will be 0, because whenever it will come to this sulfuric acid side, immediately it will be absorbed. Okay, because the sulfuric acid has a very high affinity to absorb it. So no water vapor will be available at the interface. That's mean that you can assume this pressure, that vapor pressure at L, this is equal to 0, and at that time, and total pressure, that is the 1 atmosphere equal to 1.013 bar. So this thing you should keep it in mind. 1 atmosphere will be almost equal to 1 bar, but there is some difference. 1 atmosphere equal to 1.013 bar. So, and DAB equal to 0.38 K, that semi square per second. So now I will take it in, because I want to go in MKS. Okay, so SI unit, that's why semi square to meter square. So 2, so then it will be 0.02728 into 10 to the power minus 4 meter square. Then I took this thing 1, so 10 to the power minus 5. So because I am keeping this is in 10 to the power minus. Okay. Now we know this equation. See, once you using equation diffusion of through non-diffusing B, this is my equation, and here in this case my case is gas phase. So I will use this equation directly. Okay, DAB I will use this one. So the pressure I am using in bar. Okay, temperature R I am coming. Temperature is T is this. L is that 1.2 millimeter equal to 1.2 into 10 to the power 3 minus 3 meter. Ln P equal to this. PAL okay, this is, I think this PA0 minus PAL. Okay, PA0 minus PAL. So this will be this P minus PA0, this is 1 PA0 by PA. PAL will be 0 by this will be PA. So it is wrong. So should make it correct. PAL equal to 0. No, sorry, I did mistake. This is correct. L and I made this one correct. Okay. So if you take this one, discard this one, and then so this is correct, and it will be opposite. This will come to the top, okay, and this will come to the bottom. Okay, that is very simple thing you can do. But thing is, one is R. See, unit of R is very important. Generally, people do lot of, although you know all this thing, but you should be careful little bit to choosing. R equal to, we know what, 0.082 liter atmosphere gram mole bar Kelvin. Okay, now in this case, in atmosphere, this is bar, so I will keep this 1.08 there. Now liter equal to 1 liter equal to 1 decimeter cube. Okay, so decimeter cube to meter cube, when I will came the meter cube, okay, then it will be 10 to the power 3, okay, 10 to the power 3 multiplication, and gram mole to then again 10 to the power 3. So this 10 to the power 3 it will be cancelled out. So this resulted this one. So this, then if you make this calculation, and this will be your answer. Okay, so Na equal to 1.4082 into 10 to the power minus 6 kilomole per meter square second equal to, in terms of kg, that will be this thing. So if you multiply with this molecular weight of water, so this will be your flux. Okay, so important is your problem. When problem will be given to you, you have to identify whether it is falling under diffusion of A through non-diffusion way or counter diffusion. So accordingly, and for that time, you have to see what is happening at the interface. Okay. Now, next problem, that is counter diffusion. So determine the rate of following reactions based on unit area of the catalyst. Okay, per gram means moles or kilomoles per meter square second. Okay, unit area, that means flux. Okay, rates of the following based on rate equal to kilomole per gram or volume, but when I am giving the meter square rate equal to kilomole per second rate per unit kilomole per meter square second, that's mean that it is nothing but a flux occurring on a flat catalyst surface at a temperature T, and the total pressure is, case 1 is isomerization reaction A to B, that means it is equimolar counter diffusion. So 1 mole is producing 2 mole. Dimerization reaction means 2 mole is producing 1 mole of A. So this is non-equimolar, and decomposition 3 mole of A is producing 2 mole of A producing 3 mole of B. So this is also non-equimolar. So this is the case for equimolar counter diffusion, and this is will come because here A will enter into the catalyst surface and it will go to the pore, and in the O, there will be active side, one B will be, then it will come out. So this is the counter diffusion. First case is equimolar counter diffusion, and second two B and C are the non-equimolar counter. Here it is assumed that the reaction are all diffusion control. That is, concentration of A at the catalyst surface is negligible small. This is very important statement. Now you will understand, this is the mass transfer class, but you are telling the reaction is happening and rate you are asking to calculate. See, as I told that heterogeneous catalytic reaction, here it is a blending between mass transfer and heat transfer, mass transfer and reaction engine. The reaction are all diffusion control. That is, concentration of A at the catalyst surface is negligible small. Now see what is the happening. So let's come to our previous slide. So we had the external diffusion, internal diffusion, adsorption, the surface reaction, then desorption of B, the internal diffusion of B or product, and then external diffusion. Among them, they told that the surface reaction is very fast. If this reaction is very fast, that means whenever A will reach to this surface, immediately it will be consumed, isn't it? And the rate will be determined by this diffusion, either external or diffusion. That means it is the mass transfer control. Now let's try to this phenomena with an example. Let's take one of you likes to take Rasgulla. Okay. Now what is your consumption rate? That is, let's take you have a consumption rate 10 Rasgulla per minute. So that is your capability. If I give you 10 Rasgulla per minute, you can take it. So this is your, let's take your reaction. This is this one. So I have given one thali in front of you. I am giving you, if I give you 10 Rasgulla per minute, so you will take. Now let's take, so if you take one thali, so there are two steps. One is I am giving you the Rasgulla, okay, to the thali, and then you are taking the Rasgulla. So what is your rate? Your rate is 10 per minute. Now let's take, I am giving you the 1 Rasgulla per minute. If I give you 1 Rasgulla per minute, whenever because you have a capability to take 10 Rasgulla, whenever I give the Rasgulla, immediately you will consume. So no Rasgulla will be left in your thali. Okay. So if that means this is the diffusion, this is the, I am giving you that 1 Rasgulla per this. If this is the slow state, you have all the capability, but but 1 Rasgulla is per minute coming, so immediately you will consume and no Rasgulla will be there. That's why concentration, that's why it is telling that the reactions are all diffusion control. Diffusion control means here which step will be the slow step, that will be the control. So if you see the overall rate of the reaction, so 7 steps are there. Now it is very fast step. Let's take, this is the very slow step. So although all other steps are fast steps, if this is the slow step, so overall rate will be the slow step. Let's take, if I give you 20 Rasgulla per minute, so that is then this is the first step. Now you have taken to 10 Rasgulla, so then what will happen? So then slowly in thali the Rasgulla will be dumped. But because you have a capability to take 10 rasgulla, so I am giving 20. So after certain time the rasgulla will full, the thali will be full. When thali will be, then I have to give one 10 rasgulla per month. I have to reduce this, then only you can take. So overall rate is the, what is the rate of the slow step. So in this case, if diffusion is the controlling step, that diffusion rate is the slow step than the reaction step, then this diffusion rate will control the reaction, and in that scan, this concentration at the catalyst surface, that will be 0. So this statement in the reaction are all diffusion control. That means diffusion rate is slow step, and overall and reaction rate of reaction, that step is fast. So overall rate will be the slow step one, and that will control this. That was diffusion. That is concentration of A at the catalyst surface is negligible small. The diffusion of gases occurs through a stagnant film of thickness delta. That is that what is the film thickness, that is the partial pressure of B in the bulk is PB0. Okay, so PB0 is your partial pressure of bulk. This statement is given. Now you have to calculate the fluxes. Okay, rate per unit area, rate per unit kilomole per second per unit per meter square. So how will you calculate this one? Let's take for one. The partial pressure of A and B in the bulk, let's say PA0 and PB0. Okay. Those at the catalyst surface is PAS, PBS. These are, now I know PAS, that is equal to 0 because reaction rate is very fast. So whenever A will reach to the catalyst reactive side, immediately it will be consumed. So that's why it is 0. See, with the statement you have to take this PA is equal. Similarly, we did it for the last one. Also, total P equal to PA0 and PB0. The reaction is this, Na equal to Nb at steady state. So this is the gas phase, and this is my governing equation. Okay, so Na equal to Nb minus Nb, that will cancel out Na into dz. This dAB, what we have did it once. So integration PA0 and 0 ZZ equal to this PAS, that will be 0. So Na will be RT this side. This should be delta. Now what is PA0? PA0 equal to P minus PB0. So this will be your, because you cannot express this, because in Portland statement it is telling you that PB0. So you have to express in terms of, lastly this step you should do PA0 for P minus PB0. Okay, this is the first problem. Now second problem is same, but reaction is A to 2B. That means when 2 moles of A will enter into the catalyst, 1 mole of A will come. That means the flux of A is twice of B. That means N by 2, whatever the flux of half will be NB, or Na will be 2, but in opposite side, Na equal to minus twice NB. Okay, flux of A will be twice of NB. This is the thing. Okay, at steady state. So this is my governing equation. Na equal to Na plus NB, Pa by P minus dAB by RT dP dz. So Na equal to NB will be minus N by 2. Okay, Na by 2. So put this one. Okay, then you put this Na by 2, take this side and multiply it by 2, then this will be your equation. Okay, then dz this, and you take this one, this side here, okay, P. Now 0 to Z, okay, 0 to Z, okay, will be PA0 and PS will be 0, that's del N 2P into 2P minus PA0, okay, and this dz, then Z will be N P. Now one P is one other P equal to PA0 minus PB, so it will be cancel out, so N equal to 2 DAB P, instead of D I should write it delta, okay, delta okay. So this will be your expression, so this will be flux, okay. So that's, if you see what will be the expression of non-equimolar, it totally depends on the stoichiometry of the reaction or stoichiometry of the diffusion process. So it is very case specific, but in this case equimolar, that will be always this, no problem. But that's why I told that, you know, during calculation of non-equimolar counter, we will solve with one example. So this is one example we have taken, okay. So here, but you have to start with this governing equation and you have to take this one, what will be Na equal to this thing, okay. Once you start, then you make this mathematics and then finally you will come to the solution, okay. Now C is equal to 2A equal to 3. So 2 moles of A when will come into the catalyst particle, then 3 moles of B will come. So Na by 2, okay. So this is the very simple thing you already studied in reaction engineering, okay? So whatever the flux by its stoichiometry will be it's negative, so NB by its stoichiometry is negative, because Na and these are counter diffusion, okay. So this is also Na equal to 3, Na equal to minus 2n, or NB equal to minus 3 by 2n. So now I will put this NB equal to minus 3 by 2 Na in this equation. This is my governing equation. So I put this one, NB equal to minus 3, this thing, and then if you take this way, the Na equal to plus Pa by P minus DAB to RT dP by dz. This is this one, okay. Now this is equal to, on negative sign, so it will cancel out, this will be this, and this is Pa minus Pa0 by 2P, okay. This is Pa, and this Na equal to 2AB DAB RT to put delta, okay, delta and delta, and out of this delta. So this will be expressed. So you now understand that non-equimolar counter distribution, it totally depends on the stoichiometry of the fluxes. Accordingly, you have to, that final expression will come, but you should know how to calculate. You have to take the governing equation, and governing equation you should take what way, this. Now in this case, this is gas phase that was you are taking. If somebody is given a mole fraction, you have to take that governing equation. If it is molar concentration, you have to start with that equation. That's the, okay. So today we have discussed two problems. One is based on the diffusion of A through non-diffusing B. We have taken the example of drying of air with sulfuric acid in a packed bed, but that was the case of diffusion of A through non. So that's why I am telling repeatedly, you have to see the what is happening between the interface. Two phases will be there and interface. If A is diffusing and B is not diffusing, that's mean that is diffusion of A through non-diffusing. If A is diffusing one direction and B is diffusing another direction, then it will be counter diffusion. Okay, thank you for your attention.